Hello, my dear children. Welcome to the mathematics class. Today we are going to discuss probability. In this chapter, we have discussed the concepts of 16.2 in the previous class, and we have discussed some problems on the concepts of exercise 16.2. I hope you have understood the concepts of exercise 16.2 well, and I hope you have done the sums in the exercise 16.2. Haven't you, my children? Right. Today we are going to discuss the concepts of exercise 16.3. Are you ready to listen to the class, my children? Right. Now let us discuss about axiomatic approach of probability. How to find probability of an event in this axiomatic approach. Okay, my children. Right. In earlier sections, we have considered random experiments, sample space, and events associated with these experiments. Yes or no, my children? In our day-to-day life, we use many words about the chances of occurrence of events. The probability theory attempts to quantify these chances of occurrence or non-occurrence of events. Okay, my children. The concept of probability theory attempts to try to quantify the chances of occurrence of an event or non-occurrence of events. Okay, my children. Right. In earlier classes, we have studied some methods of assigning probability to an event associated with an experiment having known the number of total outcomes. Yes or no, my children? In earlier classes, we have studied probability of an event is equal to number of favorable outcomes by total number of outcomes. Yes or no, my children? In the ninth class, we have studied the formula. Haven't you, my children? Similarly, by using the statistics, we have found the probabilities of some events in ninth class itself. That is called statistical approach of probability. That is one method of finding probability of an event. Okay, my children? Right. Axiomatic approach is another way of describing probability of an event. In this approach, some axioms or rules are depicted to assign probabilities. Okay, my children, this is another way of describing finding probability of an event. This is another method. This is another approach. This is another way to find the probability of an event. Axiomatic approach is another method. Okay, my children. In this approach, we use some axioms or some rules to assign probabilities of some events. Okay, my children. Right. We learn some axioms or rules. Now let us discuss what are the axioms and what are the rules. Okay, my children. Like, let S be the sample space of a random experiment. The probability P is a real valued function whose domain is the power set of S and range is interval closed interval 0, 1, satisfying the following axioms. Okay, my children. Here we are assuming that capital letter S denotes sample space of a random experiment and P denotes a real valued function. Function means, do you know, my children, though there is a domain and a range. Yes or no, my children? So for this probability function, domain is power set of S. Do you remember the point, my children? What is meant by power set of a set? Yes. The set of all subsets of a given set is said to be power set of the given set. Do you remember this definition, my children? Right. and the range of that probability function is closed interval 0, 1. Understood this point, my children? Means the probability of any event in a random experiment lies between 0 and 1, including 0 and 1. Okay, my children, understood this point? So, in this axiomatic approach, we are going to learn these axioms. The first axiom is for any event E, P of E is greater than or equal to 0. And the second axiom is P of S is equal to 1. And third axiom is if E and F are mutually exclusive events, then P of E union F is equal to P of E plus P of F. Okay, my children, we use these three axioms. In this axiomatic approach of probability, we use these three axioms. Okay, my children, for every event, for any event, probability of any event in the random experiment always greater than or equal to 0. It is a non-negative real number. Okay, my children. And P of S, probability of this sample space is always equal to 1. Please remember these axioms, my children. And E and F are two mutually exclusive events. Then P of E union F is equal to P of E plus P of F. In the previous exercise, we have discussed what is meant by mutually exclusive events. Okay, my children. So, if any two events are given and they are mutually exclusive events, then P of E union F, probability of union of the two events is equal to sum of the probabilities of the two events separately. We find them and we add. Okay, my children. Right. It follows from third axiom that P of phi is equal to 0. To prove this, we take F is equal to empty set. And note that E and empty set. Okay, my children. So, from this, by using this result, we prove that P of phi is equal to 0. Okay, my children. For that, we are assuming that event F is equal to empty set. Okay, my children. Then E and F are mutually exclusive events. Okay, my children. E and empty set are mutually exclusive events. Right. They are disjoint events. Therefore, from axiom 3, we get P of E union empty set is equal to P of E plus P of phi, that is equal to P of E is equal to P of E plus phi. Yes or no, my children? That is P of phi is equal to 0. Understood this step, my children? E union phi, what will you get? E only. So P of E is equal to, in RHS P of E we wrote as it is plus P of phi. Okay, my children. Now in this equation these two terms gets cancelled. P of E is in LHS as well as in RHS. These two terms gets cancelled. Then what will you get? Finally P of phi is equal to 0. Understood this point, my children? Right. Now let S be a sample space containing outcomes omega 1, omega 2 and so on omega n. That is S is equal to set omega 1, omega 2, omega 3 and so on omega n. Okay, my children, we have taken a sample space. In this sample space, omega 1, omega 2, omega 3 and so on omega n are outcomes, sample points of this sample space. Okay, my children, right. It follows from the axiomatic definition of probability that first one, 0 is less than or equal to P of omega I is less than or equal to 1 for each omega I belongs to S. Understood this point, my children? This is the first point, first axiom. the probability of any sample point is always lying between 0 and 1, including 0 and 1 also. Understood this point, my children? Right. Please remember these points, my children. Remember these axioms. Okay, my children. Right. Now, second axiom. P of omega 1 plus P of omega 2 plus P of omega 3 plus and so on, P of omega n is equal to 1. Okay, my children. Understood this second axiom? Because omega 1, omega 2, omega 3 and so on, omega n all are distinct points, sample points. Yes, my children. These are all distinct points in this sample space. Yes. So the union of all these events means P of omega 1 plus, because all are mutually exclusive events. They are distinct events, means they are mutually exclusive events. That is why the union of all these events equal to S. So omega 1 union, omega 2 union, omega 3 union, and so on, omega n is equal to S. So by taking the probability on both sides, we get probability of omega 1 plus probability of omega 2 plus and so on, probability of omega n is equal to P of S. What is the value of P of S? 1. Understood? This is second axiom, my children. Right. Now come to the third one. For any event A, P of A is equal to sigma P of omega I, where omega I belongs to n. Okay, my children. In this sample space, yes, if we define any event to A, then P of A is equal to sum of the probabilities of all these outcomes, some which are favorable to event A. Okay, my children, understood this point? Right. Note, it may be noted that the singleton set omega I is called elementary event, and for notational convenience, we write P of omega I for P of singleton set omega I. Okay, my children, understood this point? We use this notation for our convenience instead of writing this one. Okay, my children. For example, in a coin tossing experiment, we can assign the number dash to each of the outcomes H and T. Okay, my children. In tossing a coin, what are the outcomes H and T? Yes or no, my children? Yes. Now we assign the numbers to find the probability of this elementary event and this elementary event. This is sample point and this is sample. P of H. What is the P of H, my children? 1 by 2. P of T is also 1 by 2. Yes or no, my children? Right. Clearly, this assignment satisfies both the conditions. That is, each number is neither less than 0 nor greater than 1. Yes or no, my children? The probability of H and probability of T is neither less than 0 nor greater than 1. Yes or no, my children? Right. P of H plus P of T is equal to 1 by 2 plus 1 by 2. That is equal to 1. Yes or no, my children? Previously, we have discussed P of H is 1 by 2. Probability of getting tail is 1 by 2. So 1 by 2 plus 1 by 2 is equal to 1. Understood this equation, my children? Right. Therefore, in this case, we can say that probability of H is equal to 1 by 2 and the probability of T is equal to 1 by 2. Yes or no, my children? If we take P of H is equal to 1 by 4 and P of T is equal to 3 by 4. Suppose if you take P of H is equal to 1 by 4, P of T is equal to 3 by 4. Okay, my children. This is also a non-negative real number, not greater than 1, not less than 0. This is also not less than, neither less than 0 nor greater than 1. Yes or no, my children? Yes. Does this assignment satisfy the conditions of axiomatic approach? Tell me, my dear children. Suppose if you take P of H is equal to 1 by 4 and P of T is equal to 3 by 4, then this assignment satisfy the conditions of axiomatic approach? Yes, because this value is neither less than 0 nor greater than 1. This value is also neither less than 0 nor greater than 1. And sum of these two probabilities is equal to 1. Yes or no, my children? Yes. So, this assignment satisfy. Yes. In this case, probability of H is equal to 1 by 4 and probability of T is equal to 1 by 4. Okay, my children. We find that both the assignments 1 and 2 are valid for probability of H and T. Okay, my children. This is the second assignment. Previously we had discussed the first assignment. P of H is equal to 1 by 2. P of T is equal to 1 by 2. Okay, my children. Right. Both are valid assignments. In fact, we can assign the numbers P and 1 minus P to both the outcomes such that 0 less than or equal to P less than or equal to 1 and P of H plus P of T is equal to P plus 1 minus P, that is equal to 1. Okay, my children. So not only P of H is equal to 1 by 2, not only P of H is equal to 1 by 4, we can assign any number such that P of H plus P of T is equal to P plus 1 minus P is equal to 1 and 0 is less than or equal to P less than or equal to 1. Okay, my children. Not always P of H is equal to 1 by 2. Not always P of T is equal to 1 by 4, 3 by 4. Okay, my children. Understood this point? We can assign any number. This assignment 2 satisfies both the conditions of the axiomatic approach of probability. Hence, we can say that there are many ways, rather infinitely many, to assign probabilities to outcomes of an experiment. Okay, my children. Understood this point? We can assign any number to the outcomes of any experiment. We can assign probabilities to outcomes of any experiment. Understood this point, my children? Right. We now consider some examples. Let us consider some examples. Let us take some examples. Let a sample space S be set omega 1, omega 2 and so on omega 6. Which of the following assignments of probabilities to each outcome are valid? Okay, my children, some outcomes are given here. We have to check whether these assignments of probabilities are valid or not. Okay, my children. See, these are outcomes. Omega 1, omega 2, omega 3, omega 4, omega 5 and omega 6. These are outcomes. This is the assignment A, second assignment, third assignment, fourth assignment and fifth assignment. We assigned probabilities of these outcomes like this. Understood this point, my children? For this sample space, these are the sample points omega 1, omega 2, omega 3 and so on omega 6. For these outcomes in this sample space, for the sample points in this sample space, we assigned some values. Probabilities of these sample points is assigned like this. This is first assignment. This is second assignment. C is third assignment. D is fourth assignment. E is fifth assignment. Now let us check whether the first assignment is valid or not. Similarly, we check whether the second assignment is valid or not. Likewise, we check all these assignments, all these 5 assignments, whether they are valid or not for the axiomatic approach of probability. Okay, my children, understood this point? Right. Now come to the solution part. See the first assignment, condition 1, that is each of the number p of omega I is positive and less than 1. So the first axiom is satisfied in the first assignment A. If you observe first assignment 1 by 6, 1 by 6, 1 by 6 and so on. So all are positive real numbers and less than 1. The first condition is satisfied. The first axiom is satisfied. Next, condition 2, second axiom, sum of the probabilities, that is 1 by 6 plus 1 by 6 plus 1 by 6 plus 1 by 6 plus 1 by 6, that is equal to 1. So here second axiom is also satisfied. Understood this point, my children? So the two axioms of axiomatic approach of probability were satisfied by the sample points of the sample space. So we can say that the assignment is valid. Understood this point, my children? So first assignment is valid. Similarly, let us check second assignment. Condition 1. Let us verify condition 1. Each of the number p of omega I is neither 0 or 1. Yes, I mentioned. If you observe the second assignment B, then we find that each of the number p of omega I, probabilities of the sample points, is neither 0 nor 1. Okay, my children. Now, second condition. Let us check second condition. Sum of the probabilities is equal to 1 plus 0 plus 0 plus 0 and so on. So then we got 1. Therefore, the assignment is valid. The two axioms are satisfied by this assignment B. Understood this point, my children? Right. Now come to the third assignment. Let us check condition 1. Two of the probabilities P of omega 5 and omega P of omega 6 are negative. The assignment is not valid. If we observe the third assignment, that is assignment C, the probability of omega 5 and the probability of omega 6 are negative numbers. So the assignment is said to be not valid. Understood this point, my children? Right. Now come to the fourth assignment. Since P of omega 6 is equal to 3 by 2, it is greater than 1. This assignment is also said to be not valid. The probabilities of every sample point in the sample space should be lying in the interval 0 to 1, not greater than 1, not less than 1. Okay, my children, neither less than 1 nor greater than 1. But here in this case, we got 3 by 2. It is greater than 1. So this assignment D is not valid. Understood this point, my children? Right. Now come to the fifth assignment E. Since sum of the probabilities 0.1, 0.2, 0.3, 0.4, 0.5 and 0.6 is equal to 2.1. This assignment is also not valid. The first condition is satisfied, 0.1, 0.2, 0.3, 0.4, 0.5 and 0.6. All these numbers are lying in the interval, close interval 0 and 1. As I mentioned, but the sum of all these numbers is equal to 2.1. But it should be equal to 1 only. But we got here 2.1. So this assignment is also not valid. Understood these points, my children? Right. Now let us discuss probability of an event. Okay, my children, let S be a sample space associated with the experiment examining 3 consecutive pens produced by a machine, and classified as good means non-defective and bad means defective. We may get 0, 1, 2 or 3 defective pens as a result of this examination. So, my children, suppose if you have taken an experiment examining 3 consecutive pens produced by emission and classified them as good and bad. Good means non-defective, bad means defective. So what are the chances of getting bad pens or defective pens? 0, 1, 1 pen may be defective, 2 pens may be defective, 3, all the 3 pens may be defective, all the 3 pens may be non-defective. Yes or no, my children? Right. Understood these 3 numbers, my children? Right. A sample space associated with this experiment is S is equal to set BBB, BBG, BGB, GBB, BGG, GBG, GGB, GGG, where B stands for a defective or bad pen and G stands for a non-defective or a good pen. Okay, my children. So these are the outcomes. As for my children, all the 3 pens may be defective pens, or the first 2 pens may be defective and the third one may be non-defective, or first may be defective and the second one is non-defective and third one is defective. Similarly, in this case, first one may be non-defective and the remaining 2 pens, next 2 pens may be defective, or the first pen may be defective and the next 2 pens may be non-defective, or first pen may be non-defective, second pen may be defective and the third pen may be non-defective, or first 2 pens may be non-defective and third one is defective. Otherwise, all the 3 pens are non-defective. Yes or no? These are only the possibilities. These are only outcomes in this random experiment. Understood this sample space, my children? Right. Let the probabilities assigned to the outcomes be as follows. Okay, my children, let us write the probabilities of all these sample points of this sample space. Okay, my children, right. See here, my children, these are all sample points of the sample space, elementary events of the sample space, and we have written how many sample points are there? 1, 2, 3, 4, 5, 6, 7, 8. Okay, my children, so 1 by 8. Probability of this elementary is also 1 by 8. Probability of this elementary is also 1 by 8. And so on. Understood this table, my children? Right. Let event A is equal to, there is exactly 1 defective pen, and event B, there are at least 2 defective pens. Okay, my children. Now let us define 2 events, namely A and B. Event A is defined as there is exactly 1 defective pen, and event B is defined as there are at least 2 defective pens. Okay, my children. Now, can you find the elementary events in this sample space which are favorable to event A? Exactly 1 defective pen means, see here, only 1 defective pen, only 1 defective, only 1 defect. These 3 elementary events, these 3 sample points are favorable to event A. Yes or no, my children? Similarly, what are the elementary events of the sample space? Yes. What are the sample points of sample space? Yes. Are favorable to event B? At least 2 defective pens. Means there may be 2 defective pens, or all the 3 pens may be defective pens. Okay, my children. So here 2 defective pens, 2 bad pens, 2 bad pens. Otherwise, all the 3 pens may be bad, defective pens. So 1, 2, 3, 4. All these 4 outcomes, all these 4 sample points of the sample space are favorable to event B. Understood this point, my children? Right. Now let us write event A is equal to BGG, GBG, GGB, and B is equal to BBG, BGB, GBB, BBB. Understood these two events, my dear children? Right. Now P of A is equal to sigma P of omega I, comma, for all omega I belongs to A. Okay, my children, means sum of this probability plus this probability plus this sample point probability. Sum of the probabilities of sample points which are favorable to event A. We have to find the sum. Okay, my children, right. That is equal to P of BGG plus P of GBG plus P of GGB. Understood this step, my children? Right. That is equal to 1 by 8 plus 1 by 8 plus 1 by 8. That is equal to 3 by 8. We have substituted the values of P of BGG 1 by 8, P of GBG 1 by 8, P of GGB 1 by 8. Understood this statement, children? By simplifying these three numbers, we get 3 by 8. That is P of A is equal to 3 by 8. Understood this point, my children? Right. And P of B is equal to sigma P of omega I, comma, for all omega I belongs to B. Here we find probability of event B by following the same steps, by following the same procedure as we followed to find the probability of A. Okay, my children? Right. That is equal to P of BBG plus P of BGB plus P of GBB plus P of BBB. Understood this step, my children? We are writing the probabilities of these sample points, sum of the probabilities of these sample points. Okay, my children? That is equal to 1 by 8 plus 1 by 8 plus 1 by 8. That is equal to 4 by 8. By simplifying this number, what will you get here? 1 by 2. This is the probability of B. Understood this point, my children? This is the probability of this event A and this is the probability of event B. Okay, my children? Understood? Right. Now let us take another example. Okay, my children? Let us consider another experiment of tossing a coin twice. Okay, my children? Here we have taken another experiment, that is tossing a coin twice. Can you write the sample space for this random experiment, my children? Right. The sample space of this experiment is S is equal to HH, comma HT, comma TH, comma TT. Understood this sample space, my children, for this random experiment of tossing a coin twice? These are only the outcomes. Yes or no, my children, in tossing a coin twice? Right. Let the following probabilities be assigned to the outcomes. Okay, my children. Let us consider the probabilities of these sample points are assigned as follows. Okay, my children. Right. P of HH is equal to 1 by 4. P of HT is equal to 1 by 7. P of TH is equal to 2 by 7. P of TT is equal to 9 by 28. Like this, here we have assigned, we have not found here directly, we assigned these values to these sample points of this sample space. Okay, my children, for every element, for every elementary event in this sample space, we have assigned the probabilities like this. Okay, my children. Now, in this axiomatic approach of probabilities, the conditions are satisfied or not. See here, this is neither less than 0, not greater than 1. These probabilities, observe these probabilities, my dear children. All these probabilities are neither less than 0, not greater than 1. So the first condition of axiomatic approach to the probability is satisfied. And the sum of these probabilities, if you find the sum of all these probabilities, will you get 1 or not? Yes, we can get the sum of all these probabilities equal to 1. So the conditions are valid. This assignment is valid. Okay, my children. Clearly, this assignment satisfies the conditions of axiomatic approach. Yes or no, my children? The two conditions are satisfied by this assignment. We assigned these properties. We have not found the properties of these sample points of this sample space. Yes. Okay, my children. Directly we assigned these properties. Understood this point, my children? Right. Now, let us find the probability of the event E. Both the tosses yield the same result. Here E is equal to HH, TT. Yes or no, my children? Here we are finding the event of event E. And event E is defined as both tosses yield the same result. Means both times we get head or both times we get tail. These are the outcomes favorable to event E in this sample point. Yes or no, my children? Right. Now let us find the probability of event E. So P of E is equal to sigma P of omega I, comma, for all omega I belongs to E. Okay, my children, understood this point? Right. That is equal to P of HH plus P of TT. Here, what are the outcomes favorable to event E? HHTT. Okay, my children, then what is P of HHE? 1 by 4. What is P of TT? 9 by 28. Okay, my children, understood this point? We are adding the probabilities. Now 1 by 4 plus 9 by 28. Understood this step, my children? Just we substituted these two values in this expression. Okay, my children? Right. By simplifying these two numbers, we get to 4 by 7. 4 by 7. This is the probability of event E in this sample space, in this random experiment. 4 by 7. Okay, my children? Right. For the event F, exactly two heads. We have F is equal to HH and P of F is equal to P of HH, that is equal to 1 by 4. Suppose if you take another event F such that exactly two heads, F is defined, event F is defined as exactly two heads. Then what are the elementary events in the sample space S favorable to event F? Only HH. Yes or no, my children? So P of F is equal to P of HH. What is the value of P of HH? 1 by 4. Understood this point, my children? Here also we found the probability of event F. Here we found probability of event E. Understood this point, my children? Right. Next, probabilities of equally likely outcomes. Now we are going to discuss probabilities of equally likely outcomes. Okay, my children? Right. Let a sample space of an experiment B, S is equal to set omega 1, omega 2, omega 3 and so on omega n. Let us consider this is the sample space for a random experiment. Okay, my children? Right. Let all these outcomes are equally likely to occur. That is, the chance of occurrence of each sample point must be same. Okay, my children? In the previous example, we have taken the probabilities of the elementary events of the sample space are not equally likely. As on my children, P of HH is 1 by 4, P of HT is another number like this. But here we have taken all these outcomes, all these elementary events, all these sample points of the sample space are taken as equally likely to occur. That means the chance of occurrence of each sample point is same. That means P of omega 1 is equal to P of omega 2 is equal to P of omega 3 is equal to and so on P of omega n. Understood this point, my children? Right. That is P of omega I is equal to P for all W omega I belongs to S, where 0 less than or equal to P less than or equal to 1. Okay, my children. For all these elementary events, probability is the same, small letter P. We have taken as a small letter P. Probabilities of every sample point in the sample space is same. Okay, my children. Right. Since sigma P of omega I is equal to 1, we know that the sum of the probabilities of elementary events of the sample space is equal to 1. Okay, mention sigma P of omega I is equal to 1. Okay, mention understood this point? Right. This is the second axiom in the axiomatic approach of probability. This is the second axiom. Okay, mention P of S is equal to 1. Okay, mention this implies P plus P plus P plus and so on n times is equal to 1, because we have taken P of omega is equal to P. So P plus n times is equal to 1. Understood this step, my children? Right. This implies NP is equal to 1. So now, my children, by simplifying all these terms, what will you get? NP in LHS, that is equal to 1. Understood this step, my children? Right. This implies P is equal to 1 by N. Okay, my children, here we got the probability, the P value 1 by N. Okay, my children, when all the outcomes are equally likely, then the probability of the every element is equal to 1 by N. Okay, my children. Right. Let S be a sample space and E be an event such that N of S is equal to N and N of E is equal to M. Okay, my children. Let us consider N of S is equal to N and N of E is equal to M. Then, if each outcome of the sample space are equally likely, then it follows that P of E is equal to M by N. That is equal to number of outcomes favorable to event E by total number of outcomes, total possible outcomes. Okay, my children. This formula is learned. This was learned in earlier classes itself. So, my children, when the events of a sample space are equally likely, then we can find the probability of the event E is equal to number of outcomes favorable to event E by total possible outcomes. Okay, my children. Right. Now, let us discuss probability of the event A or B. Okay, my children, A or B, how do you denote? Yes, A union B. Yes, sir, my children, in the previous classes we have discussed event A or B is denoted by A union B. Okay, my children, let us now find the probability of the event A or B, that is P of A union B. Okay, my children, right. Let A is equal to HHT, HTH, THH, and B is equal to set HTT, HTH, THH, HHH. Be two events associated with tossing a coin thrice. Okay, my children, here we assumed, we defined two events, namely A and B, like this. Now let us find the probability of A union B. Okay, my children, right. Clearly, A union B is equal to, here we are finding the union of these two sets. Then what will you get? Set HHT, HTH, THH, HHH. Yes, sir, my children. Here we are using the previous knowledge of set theory. Okay, my children. Right. Now, P of A union B is equal to P of HHT plus P of HTH plus P of THH plus P of H, H, H. We are adding the properties of all these elementary events which are favorable to A union B. Okay, my children, by using the previous knowledge, the previous slides we have discussed like this. Yes, sir, my children. Probability of an event is equal to sum of the probabilities of all the elementary events which are favorable to the given event. Okay, my children, right? That is equal to, if all the outcomes are equally likely, then P of A union B is equal to 1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8. That is equal to 4 by 8. That is equal to 1 by 2. If you assume that if all the outcomes of this random experiment are equally likely, then we get 1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8. That is equal to 4 by 8. Understood this statement, children? Right. Also, P of A is equal to P of HHT plus P of HTH plus P of THH. As I mentioned, that is equal to 1 by 8 plus 1 by 8 plus 1 by 8. That is equal to 3 by 8. Understood this step, my children? Similarly, let us find P of B. And P of B is equal to P of HTH plus P of THH plus P of HHH. That is equal to 1 by 8 plus 1 by 8 plus 1 by 8. That is equal to 3 by 8. Understood this step, my children? P of A value and P of B value. Okay, my children? Right. Therefore, P of A plus P of B is equal to, what will you get here? 3 by 8 plus 3 by 8. That is equal to 6 by 8. That is equal to P by 4. So, P of A plus P of B is equal to 3 by 4. Whereas P of A union B is equal to 1 by 2. Yes or no, my children? Right. It is clear that P of A union B is not equal to P of A plus P of B. Yes or no, my children? Right. Here these two numbers are not equal. These two probabilities are not equal. Understood this statement, children? Right. The points HTH and THH are common to both A and B. Yes or no, my children? In the computation of P of A plus P of B, the probabilities of the points HTH and THH, that is the elements of A intersection B, are included twice. Yes or no, my children? That is why we got more number. P of A plus P of B is more than the P of A union B. Yes or no, my children? Right. Thus, to get the probability P of A and B, we have to subtract the probabilities of the sample points in A intersection B from P of A union plus P of B. Okay, my children? Right. That is, P of A union B is equal to P of A plus P of B minus P of A intersection B, or sigma P of the omega I for all omega I belongs to A intersection B. Okay, my children, we are subtracting these probabilities from this probability. Okay, my children, that is P of A plus P of B minus P of A intersection B. Okay, my children, please remember this formula. P of A union B is equal to P of A plus P of B minus P of A intersection B. Same as in the case of set theory, we have found N of A union B is equal to N of A plus N of B minus N of A intersection B. Do you remember that formula, my children? Right. Similarly, we are using the same formula in the case of probabilities. P of A union B is equal to P of A plus P of B minus P of A intersection B. That is why I told you at the beginning of this chapter, we are linking the set theory knowledge to find the probability of an event in this axiomatic approach. Okay, my children. Thus, we observe that P of A union B is equal to P of A plus P of B minus P of A intersection B. Okay, my children. Please remember this formula. This is very useful formula. Okay, my children. Right. The above result can further be verified by observing the Venn diagram. See the figure 16.1, my dear children. Figure 16.1. See, in this Venn diagram, here we are using the set theory knowledge. Here A and B are two disjoint sets. Okay, my dear children, means they are mutually exclusive events. Then A intersection B is equal to 5. Okay, my children, if the two sets are disjoint sets, then A intersection B is equal to 5. But here, in this case, in this Venn diagram, we have not taken the two sets A and B are disjoint. They are not disjoint sets. A and B are not disjoint sets. Some part is a common part is there. A intersection B is there. Okay, my children. Therefore, P of A intersection B is equal to P of 5, that is equal to 0. In this first case, if you take P A and B are disjoint sets, in that case P of A intersection B is equal to 0. Understood this point, my children? Right. Thus, for mutually exclusive events A and B, we have P of A union B is equal to P of A plus P of B. Okay, my children, if A and B are mutually exclusive events, in that case P of A union B is equal to P of A plus P of B. But on the other hand, we can find P of A union B by using this formula only. P of A plus P of B minus P of A intersection B. Okay, my children, which is axiom 3 of probability. Okay, my children, this is the axiom 3. If all two events are mutually exclusive events, then P of A union B is equal to P of A plus P of B. This is the third axiom of axiomatic approach of probability. Okay, my children. Right. Now come to the last point, that is probability of event not A. Okay, my children. Right. Consider the event A is equal to 2, 4, 6, 8 associated with the experiment of drawing a card from a deck of 10 cards numbered from 1 to 10. Okay, my children, right. Clearly, the sample space is S is equal to set 1, 2, 3 and so on 10. Yes or no, my children? Right. Understood these steps, my children? We have considered an event A is equal to set 2, 4, 6, 8. The random experiment is drawing a card from a deck of 10 cards numbered from 1 to 10. Then sample space is 1, 2, 3 and so on 10. Understood this sample space, my children? Right. If all the outcomes 1, 2, 3 and so on 10 are considered to be equally likely, then the probability of each outcome is 1 by 10. As I mentioned, suppose if you consider all the outcomes of this sample space are equally likely, then probability of each element of this sample space is 1 by 10. Yes or no, my children? Right. Now P of A is equal to P of 2 plus P of 4 plus P of 6 plus P of 8. Yes or no, my children? Right. That is equal to 1 by 10 plus 1 by 10 plus 1 by 10 plus 1 by 10. Because we have assumed that all these events are equally likely events. So the probability of this event is 1 by 10, probability of this event also 1 by 10, probability of this event also 1 by 10, and probability of the event also 1 by 10. Understood this statement is done. By simplifying all these four numbers, we get 2 by 5. Understood this statement is done. Right. Also, event not A is equal to A dash, that is set 1, 3, 5, 7, 9. Do you remember that, my children? Complementary set. Yes. So here A dash, that is A complement. This is nothing but A complement is equal to S minus A. Yes or no, my children? Then we get 1, 3, 5, 7, 9. Understood this step, my children? Right. Now P of A naught, P of A dash is equal to P of 1 plus P of 3 plus P of 5 plus P of 7 plus P of 9 plus P of 10. Okay, my children, understood this step? Right. That is equal to 1 by 10 plus 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 1 by 10. That is equal to 6 by 10. That is equal to 3 by 5. Understood this step, my children? P of A complement is equal to 3 by 5. We got here P of A is equal to 2 by 5. Okay, my children. Now we derive the relation between P of A and P of A complement. Okay, my children. Thus P of A complement is equal to 3 by 5. That is equal to 1 minus 2 by 5. That is equal to 1 minus P of A. This 3 by 5 can be written as 1 minus 2 by 5. Yes or no, my children? That is equal to 1 minus 2 by P of A. Yes or no, my children? So P of A complement is equal to 1 minus P of A. P of A dash is equal to 1 minus P of A. Understood this point, my children? Right. Also, we know that A complement or A dash and A are mutually exclusive events. A complement and set A both are mutually exclusive and exhaustive events. That is, A intersection A complement is equal to 5 and A union A complement is equal to S. As for the mention, understood this step? Right. Or P of A union A complement is equal to P of S. Okay, my children, we are taking probability on both sides of this equation. Then we get P of A union A complement is equal to P of S. Okay, my children. Now P of A plus P of A complement is equal to 1 by using axiom 2. P of S is equal to 1. Yes, my children. And using the third axiom also, two mutually exclusive events. So finally we got P of A complement, P of A dash is equal to P of not A, that is equal to 1 minus P of A. Please remember this formula, my children, well. Okay, my children, these are the concepts for this exercise 16.3. Okay, my children, right.